Okay, so problem 32 is Pandigital Products. Now I've not actually done this one before, and I have a feeling this might take a while. But yeah, let's get into it. It's pretty difficult to understand the first time we read through this, but from what I gather, what we basically want to do is have a number where 8 and 2 of its factors, so for example this number right here has these 2 factors, it might have others, but these 2 in particular, between the 3 numbers all contain the digits 1, 2, 3, 4, 5, 6, 7, 8 and then 9, contain them all and only 1 time each. So we need to find the sum of all products whose multiplicand, multiplier and product identity can be written as a 1 through 9 pandigital. So yeah, let's have a go. What I think we're probably going to do with this is take so if we're doing 1 through 9, obviously these numbers are limited to being 9 digits long. They're also not going to quite be 9 digits long because obviously you need a number that then has other numbers multiplying into it. So it's going to be I think 7 digits. So it's going to be able to limit 6 digits, so that you can have a 3 by 3 times into a 6-digit number. So I'll probably limit it to 7 digit numbers. Now if we do that, we could just brute force through all the numbers and then for each one factorize and check the factors to see if any of them produce this pandigital property. Not sure how efficient that's going to be because factorizing these numbers is going to take a while, but since we're only doing 7-digit numbers, it should be fine, I think. So probably going to start like that, try and brute force it, and if it doesn't work, I don't know, I'll have a rethink and try and be a bit cleverer. So we're going to need a couple of functions here. We're going to need a function to return factors. So this is going to be Factorize. It's going to take in n, and it's going to return a list of factors. So list of factors is initially going to be empty. Oops. Okay, so we're going to say divisors is equal to divisor is equal to, we'll say 1. Now while divisor is actually, do we need to do this? No, we don't need to do this. We can do this in a for loop without a divisor. So we could say for divisor in range n, if n mod divisor is equal to 0, then we've just found a divisor. So list of factors dot append, and we're going to append our divisor. If not, doesn't worry, just skip on to the next one, and then that should be it. So what I'm going to do here, I'm just going to print the list of factors, get rid of these extra rows, and now we'll just call this function on a couple of numbers and just check how it works. So first one we'll check is 6. Okay, so we get 0 and 1. Why don't we get 2 and 3 and so on? Oops, I put a and sign there, I think. Should have been a percent sign. And I need to get rid of the oops, not there. The range containing 0. And just 1 second while I plug my headset a charge. You probably heard that beep a second ago. Whoops. Okay, so save that, run that, 1, 2, 3, So we don't include the actual number in this, but that's not an issue, since we're going to be checking the digits. If we go back to the original question, we're going to be checking the digits at the end and seeing that we have like a unique set of 1 to 9 digits. So obviously if you have the number in there as a multiplier, then you're going to have 2 of all the numbers, all the digits that are contained in the number, if that makes sense. For that reason, we can actually get rid of the 1 as well. So if we start at 2, this will work a little bit nicer. So we get 2 and 3 here. So there's step 1 done. Let me just try a couple of different numbers. So let's try 20. And now I just want to see performance wise, and can it factorize something like this? Okay, pretty quick. Obviously that number was, oh no, yeah, okay. What I will do to increase performance, I think, should I do this? I'm thinking we should only check up to the square root of n, and then just append like the factor, and then at the end, once we have all the factors, we could create a new list where we pair all the factors with their corresponding pair, and then like we could return this as pairs, because obviously we need them in pairs eventually anyway. So I'm going to rename this as find factor pairs. Wow, I butchered that. Okay, so in range 2 to n to the power of a half, so the square root of n. We actually want to floor this, so we're just going to import the math module in a sec. I'll import it right now actually. Import math. Then we want to do math.floor, and then we want to do we want to add 1 to this to make sure we include the square root possibility, although that's not important since we don't care about those. Let me just see what this is going to do. Factor, alright, okay. So I'm expecting this to run way quicker, not that we'll notice because the other one was quick enough. And yeah, you see we just get half the factors now. I just want to try this with a square number, so let me try it with 25. I just want to see if it actually returns the 5. Yeah, it does. Okay, so what we're going to do now is say so with our list of factors, once we get to this point, we're going to say for factor in list of factors, we're going to need a new list, so it's going to be list of factor pairs. It's going to be empty list. List of factor pairs dot append, and then we're going to want to append, because this can basically be a list of lists, and each sub list is going to be a pair. So one of them will be factor, and the other one will be n mod the factor. No, is that right? No, n divided by the factor, sorry. So if I print out below here list of factor pairs, you should see we get 5, 5 for this. We just need to change this to an int. We don't actually want any floats in here, not that it matters, but I just don't like looking at floats when I don't need to. Okay, so 5, 5. Now if we change this number to something that has more factors, oh, actually we change it to 6 first, so you'll see it should return 2 and 3 as a pair though. These aren't as separate factors, look, these are in a pair. Now let's do it with something with more factors, so we'll do like, I don't know, 20. Should get a couple of different pairs. So yeah, we get 2 and 10 as a pair, and then we get 4 and 5 as a pair. Okay, so this is pretty handy. You can start using this. So let's get rid of the print, get rid of the call, we don't need that anymore. Now we're going to need another function. So once we find these factor pairs, we need to take the number and take the, I'm probably doing this in a backwards order, we should probably just define main and take a look at what we're doing first. Just so it makes a bit more sense on video, because I know what I'm doing, but obviously it might not come across very well if I'm not showing it all. So I said we're going to check up to 7-digit numbers, okay? So what we're going to do, we're going to have, I'm going to call it a limit is equal to 1 with 1, 2, 3, 4, 5, 6 zeros following it. So to make this more readable, I've mentioned this in a previous video, but we're just going to shove these in. This is 1 million. So this is 1 million. 2, 3, 4, 5, 6, 7. Yeah, so I'd only leave like 2 digits left over. So yeah, we're not going to get any 7-digit numbers coming out with this property. So I'm pretty sure this limit is significantly lower, but we're going to use this just to be safe. So once we've got our limit, we need the sum of all products. See this language, what is this language? Let me have a look. We've got find the sum, so add together, of all the products. Products means you're multiplying them. Use multiplicand multiplier. Product identity can be written as a 1 through 9 Pandigital. So we're multiplying together what? Oh, okay, maybe it means the product this. So what it wants us to do is sum together all the numbers that can be wrote in this way. So it doesn't care about the factors, it just wants the sum of the ends. Okay, I think I get it. Maybe I'm just stupid, maybe this is obvious, but we'll see. So, I'm gonna have total is equal to 0. Now, next up we're gonna have our for loop. So, for number in the range limit, and we're gonna start at 1. And this is like obviously we're not going to get any of these properties before we hit like higher numbers, because it needs to obviously produce 9 digits total across 3 numbers. So yeah, but anyways, I'll just do them all. It's not going to take too much more computation. Some products can be obtained in more than one way, so be sure to only include it once in your sum. Okay, so we're going to have find factors and return the pairs. So we've already done that function. We've spelling pairs completely wrong. Then we're going to want to check if a given pair and the number are pandigital, so they contain all the digits 1 through 9. If they do, if they do, add the number to the total. Okay, so find the factors and return their pairs. So we're going to say list of factor pairs is equal to find factor pairs of number. Nice and easy. Check if a given pair and the number are pandigital. So to do this, we're going to have to loop through our list of factor pairs, and then for each one say, does this pair and the number produce a pandigital number? And if it does, we're going to add our number to it, and then we're going to break because we don't want to add the number multiple times, as the hint down here points out. So yeah, we need a pandigital check. So if Pandigital check on the number and the actually I need this in a loop. So for pair in list of factor pairs, if Pandigital check on number pair comes back true, then we're going to want to say total plus equals number, and then we're going to want to break out of that loop. So we've actually just done this step down here, and then right at the end print total. Now we're going to define this Pandigital check function right here. It takes in the number and pair. So what this is going to do is it's going to return true or false, and it's going to do so by saying so string number equals string number. Now actually we could say string, let's just call it string digits, I guess, and we could say for factor in string digits plus equals string of the factor. Hoping this works. Let's just print out the string digits, and then let's call this function, so Pandigital check. We're going to pass in, let's just say 4, and the pair is going to be 2 and 3. So obviously these numbers aren't right, but I'm hoping that we'll print out these numbers, so we should get 4, 2, 3 printed out, all in one line. Yeah, there we go. So hopefully you see what this is doing. It's taking in all the numbers. It's now just going to put them all in one string so that we can check the string for all the digits we need. Okay, so now we're going to say, because there's some checks we can do on this, obviously we want it to be all the digits 1 through 9, and we want it to be 1 through 9, no repeats, so it needs to be 9 digits long, and it doesn't include a 0. So if len of the string of digits is equal to 9, then we can continue. So what we'll do here is we'll just say if it's not equal to 9, then return false. Now if it is equal to 9, we could say if there's a 0 in there, return false, because apparently Pandigital doesn't include a 0. So we could say I'm not sure if this is actually going to increase our computation time or decrease, because I was hoping it would decrease, but if it's going to increase, there's no need to put this in. This is just, yeah, probably no need to put this in actually. Okay, so it's a quick Google search. Okay, so I just want to test a few things and say, like, if 0 in string digits, let me just comment this out, so otherwise it's never going to hit there. Print print contains 0. And I just want to call this Pandigital check 1, 4 and 0 and 3. I'm hoping this will print out contains 0. Yes, it does. Now what about if 0 or 1? Obviously a 1 isn't in there. I want to know if it needs any or all signifiers. Okay. So we're going to have to loop over strings. I'm going to say like digits equals, then we're going to have a list of digits. Something like this. Oops. Okay, so we've got a list of digits. We're going to take the 0 out so 0 doesn't count, remember? And we're going to say, just going to get rid of this, for digit in digits if digit not in our string digits, return false. So when we couple this with this, this is going to check to make sure it's only 9 characters long, and then this down here will check if it contains all the digits 1 through 9. Now if it contains all the digits 1 through 9 and it's only 9 characters long, then it must be Pandigital, and it means it's got one of every one. So we can now just return false, return true, sorry, down here. So if I just print the result of this, we'll test it a couple of times. So we get false for this correctly. Now if I get rid of this and add a 1, I just put in a 2 and a 5, 6, 7, 8, 9 here, should get a true. I do. Good stuff. Yeah, so call main here, and should be good to go. Let's just run it and find out. Int object not iterable. 28. So apparently pair's been passed in as an int. Just gonna print pair right here and see what's going on. So we get a 2. Why is 2 not a list? Just comment this out. And then print find factor pairs of 2, because I think 2 is the problem number. Empty. Okay, so I up this to start at 3 maybe. No, let's give it a 1. What I'll do is if pair, how's it even getting to here? Shouldn't actually get to there for 2. Let me just print out number right here. I'm gonna say that this is number. Okay, then uncomment that. Comment this. Let's try that. Okay, so number 4 fails. 4 gives us a 2. Right. So now if we change these comments back around, shot 4 in here. Let's see what this returns. So it's returning 2 as a list, but it's not a list of lists. No. Okay, because I'm returning the list of factors here and not the list of factor pairs. So I forgot to update that when I added in this new logic. So if I just run that now, I should get a pair. Yeah, I get 2 and 2. Obviously, no, that's actually, wait, I was going that. Okay, so hopefully this works. There we go. Right, now let me just take out these prints. Otherwise we'll be here all day. This is going to take too long. What I'll do is if number mod so 10,000 is equal to 0, print time at time minus start time. Okay, so it's doing 10,000 numbers every, and it's slowing down because of the factorization needed. Shouldn't take too long though, I don't think. Maybe if we change this to 100,000, we'll see a bit clearer. So 2 seconds for 100,000, that's obviously 10% of the way. 3 seconds for the next 100,000, 4 for the one after that, 5 for the one after that. Okay, so it's going to get done, it's just going to take a little while. Pretty sure we can drop this limit like by quite a bit, but I'm just going to leave it there for now and we'll run this, get the answer, and then I'll see what improvements we can make. Really slowing down now. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. So 45,228. Let's go take a look. 45,228. 7628. Awesome. So one thing I'm interested in is, can we drop this this huge number here? It'd be 100,000 instead, maybe? Yep, we can. So what I want to do is, quite like to find an upper bound on this. I have a feeling it's like something around this area. Wow, it's possibly even smaller. Not going to be lower than 1,000, surely. No, because we don't get enough digits now, because 1,000 is obviously roughly 32 point something squared, something like that. So yeah, there's not enough digits between like the product of it. So pretty sure, yeah, we do actually need the 10,000 pretty much. So 9,000 includes all of them. 7,000 doesn't. Does 8,000? 8,000 does. So all of them are below 8,000. Would be an easy way to just find the biggest one, but yeah. In fact, let's do that. Let's find out what the biggest one is. So when we find a number, print out the number. So here's all the numbers that are that have this property. So 7254 was the example given. See, we do find that. And 7852 is the biggest one. I should have known that the numbers would all be 4 digits, because you can see here this one's 4 digits. It's pretty obvious that they're all going to be, if this one is. You need 4 digits, 2 digits and 3 digits to make it. Yeah, 333 obviously isn't going to work because a 3 digit times a 3 digit does not equal a 3 digit. And 3 times a 2 is always a 4 digit number, I believe. Must be, surely. I think so. Anyways, enough of that. There's a problem done. Hopefully, if any of you are stuck, that helped out. It's pretty interesting. I've not done that one before, so yeah, first time for me. Hopefully you enjoyed the video. If you did, leave a like. Feel free to leave a comment, any suggestions if you know how to improve the speed on this. But yeah, that's it for this one. Thanks for watching, and I'll see you in the next video.